This is lecture 2 for week 3, and we're looking in this lecture at random graphs and the Watts-Strogatz model. A random graph is a graph where edges are assigned a probability measure, p. We often denote these graphs by G parentheses n comma p. Of course, if p is equal to 1, that means every edge has probability 1, or 100% chance of being there. So if p is equal to 1, we have the complete graph. And if p is equal to 0, we have the empty graph. And for all values between 0 and 1, we have some edges are there and some are not. Now, for a given fixed p, the graph GNP is not unique. For example, if p is 0.5, each edge has a 50-50 chance of being there. So if you generate it once, and then you generate it again, you would not necessarily get the same graph. So for a given fixed p, you get a collection of graphs. Unless, of course, if p is 0, you just get a single graph, or if p is 1, you get a single graph. The higher the p, the more dense the graph, and the lower the p, the more sparse the graph for the graphs in each collection. Now, if you look for a given fixed p and then find the average degree, how are the edges distributed across a random graph? Well, the number of edges in general you can think of as n choose 2, all possible edges, times p. But what is the distribution of the edges? Since this is a normal or Gaussian distribution, then what you would see is this normal or bell curve, so to speak. So the degree distribution follows a normal distribution. For example, if the average degree is 10, then most of the vertices would obtain that average. You would have fewer and fewer that are below average and fewer that are above average. And most of the edges would have the average, or vertices would have average degree. Now this is quite different from a small world graph. If you look at, say, the green bars, and that represents low degree, then you have the number of nodes that have low degree is less than those that have the average degree, like we just discussed. However, for a real-world network, many of the nodes have low degree. And then you have few nodes that are in an average and even fewer that are high. So it's a very different distribution. So what this says, and it's really very interesting if you think about it, the networks that emerge, that model real-world situations, are not random. If we look at the bar graph of what we studied last time, the TR regular graphs, what would it look like? Well, we would only have 2 bars. In some sense, you would say it's small world because most of the vertices, a larger number of vertices, have low degree, and then a collection of vertices have high degree. So we are talking now about small world graphs and the clustering coefficient and the average path length. And one thing that we can say about the clustering coefficient is that it is a local property. That is, it is a measure of a vertex, such as the degree of a vertex. So in order to make it a global property, that's why we have to add them all and then divide by the total number of vertices. This is also true for the degree. The degree is a local measure, and so we choose either maximum degree, minimum degree, average degree, in order for it to become a global measure. On the other hand, the average path length is a global property. Now let's look at the Watts-Strogatz model that was introduced in a paper by Watts-Strogatz, and they were the ones that coined the small world terminology. They began with a regular graph. And the regular graph, they said, had high clustering, but it had also a high average path length. So if you look at each vertex, its neighborhood is more dense than with respect to the entire graph. It's adjacent to those around it and not those away from it. So each neighborhood has a relatively high clustering coefficient, but the average path length is also high. If you take any pair at random, you're going to have to go around the circle to reach the other, from one vertex to the other. So both values are high. The clustering coefficient is high, and the average path length is high. By rewiring with a given probability P, if P is low, some of the edges will be rewired. And as P increases, where P this time is the probability that an edge will be rewired. As when P is 1, you have the completely random graph. When P is 0, for their model, you have the completely regular graph. And by rewiring the graph with a probability P, that means an edge will be repositioned, you obtain a small world graph. So, in this sense, we can say that small world is between regular and random. Again, if you think about the fact that when the graph is regular, that both values, the clustering coefficient and the average path length, are high, what happens in a small world is we want the clustering coefficient to be high, but the average path length to be low. So when we rewire a few of the edges, we're able to maintain sufficiently high clustering because we haven't rewired very many. But just the rewiring of some of the edges brings the average path length down. But if we continue to rewire, we lose the high clustering coefficient. We want the clustering coefficient high and the average path length low. So that's what I'm saying in here, that this process changes a regular graph to a random graph by increasing the probability that an edge will change its adjacency. Now the question arises sometimes, how high is sufficiently high? You say we want a high clustering coefficient and a short average path length. So one way to answer this question is what we've done in the preceding slide, is to compare a small world graph with a random graph. So one definition of clustering coefficient, for it to be high enough, is to say that it is higher than what you would get for this if you took the random graph with the same number of vertices. And that is also true for the average path length. The average path length should be lower than what you would get if you took a random graph on the same number of vertices. So this concludes our lecture on random graphs and another look at small world graphs using the Watts-Strogatz model.